The universe could be an illusion, a reflection. Physicist Nikodem Popławski has this idea that our universe might have formed inside a black hole. It's a serious hypothesis. It changes how we see reality. We're looking at one of cosmology's big mysteries, the possibility we're living inside an event horizon. After this, the night sky might look different. You might question existence itself. There's a famous scientific paradox. It suggests we're missing a fundamental truth, and the oldest light in the cosmos. That light might carry an encrypted message. A message from outside. What part of reality are you willing to question? That edge of the waterfall. It's a good way to picture it. It's not a wall you could touch. It's a line, a mathematical line in space and time, and it's defined by one rule. Gravity there is so strong that the escape velocity, the speed you'd need to get out, is faster than light. And nothing goes faster than light, so nothing gets out. Not a particle, not a bit of information. It's a one-way door, but the real strangeness, that's what happens when you cross it. What it does to reality. Because space and time in Einstein's relativity, they aren't a fixed stage. They're a fabric that can be warped by mass. And at the event horizon, that warping becomes extreme. So extreme that space and time they flip. Outside, you move through space. Time moves forward, you can't stop it. Inside, the direction toward the center, that's no longer a place you move through. It becomes your future. Every path, every choice points you toward that center, the singularity. Space flows inward like a river over a falls, and you're carried. The implication is profound. For someone who's crossed the horizon, the entire outside universe, it's not a place they could go. It becomes a moment locked in their past, a memory they can't revisit. It creates a self-contained reality, a room, a cosmic room, and the walls of that room aren't made of matter. They're made of physics, the fundamental rules, and if you were born inside that room, you'd have no way to perceive the walls. You'd just accept that the universe has limits. Certain horizons you can never see beyond. So that's the first piece, the unsettling piece. The defining feature of a prison like that, it would be invisible by its very nature. This paradox, it was a sign something was broken. For decades, it wasn't just a puzzle. It felt like a direct challenge to reality itself. It starts with a principle from quantum physics. Information, the details that make one particle different from another, can never be truly erased. It might get scrambled like an egg, but in theory you could trace it back. You could unscramble it. That's a sacred rule. Then Stephen Hawking showed black holes aren't completely black. They leak energy slowly, a faint whisper now called Hawking radiation. And over immense stretches of time, a black hole can evaporate. It fades into nothing. So the devastating question: when that black hole is gone, what happened to all the information? Every star, every planet, every atom that fell in. General relativity says it's crushed into the singularity, lost forever, gone. That violates the quantum rule. It means one of our two most successful theories is wrong, or at least incomplete. This was the information paradox. It suggested black holes weren't just cosmic objects. They were cosmic mistakes, places where the universe's own rulebook broke down. Physicists fought over solutions. One brilliant idea, championed by thinkers like Leonard Susskind, was the holographic principle. It proposed all the information about what fell in wasn't lost inside. Instead, it was smeared like a hologram, encoded in 2 dimensions on the surface of the event horizon itself. The 3-dimensional interior was just a projection, a shadow, but there's another possibility, more mind-bending. What if the information isn't lost because it never actually goes away? What if, when something crosses an event horizon, it isn't erased, it's just translated? This is where the story turns back on itself. If our universe is inside a black hole, then the information paradox takes on a new meaning. The matter that formed our cosmos didn't vanish into oblivion. It became everything we see. Every atom in your hand, every photon of starlight, carries the encoded information of whatever fell into that parent black hole trillions of years ago. The paradox isn't a bug, it's a feature, a clue, screaming that black holes aren't endpoints, they are beginnings. The idea of a black hole as a dead end, that's an illusion. It's not an end, it's a transformation. So every black hole could be the start of a new universe. That's called cosmological natural selection. The singularity, that point our physics breaks down, it might not be the final state. At the moment of collapse, quantum effects could cause a rebound, a bounce, like compressing a spring with incredible force and it recoils. That recoil from inside the black hole could be a big bang. Smolin took this further. He thought universes might evolve. If a universe makes many black holes, each one could spawn a new cosmos, and there could be variations like reproduction. The offspring universe might have slightly different constants, a stronger gravitational force, a different speed of light. Universes better at making black holes would have more cosmic children. Our universe with stars that form black holes might be particularly fertile in this grand multigenerational tree. The environment inside the event horizon is the key. From outside, it's destruction. But from inside, the conditions of extreme density and curved space are mathematically identical to the first moment of our own Big Bang. The horizon isn't a wall, it's a reset, a boundary that separates one set of physical laws from another. It transforms the ash of a dead star into the primordial fire of a new beginning. So black holes aren't destroyers, they're creators. Our entire cosmos, all its galaxies, might be the offspring of a single stellar collapse in a parent universe we can never see. Every time a massive star ends its life, it might not be a funeral, it could be a birth. Our existence is a legacy. We are the children of cosmic death, living in the expanding aftermath of a bounce that happened from within an event horizon trillions of years ago. It gives a meaning to the cycle of the stars. They live, they die, and in their passing, they sow the seeds for new realities. But the universe feels so vast and flat. It feels flat, yet if it's a closed sphere, why, it's the geometry of deception. You stand on a huge plane. The ground is flat under your feet. The horizon is a straight line. But you're on a sphere, you're on a planet. Your local view deceives you about the whole shape. Our observable universe is like that. The part we can measure looks remarkably flat. Light from the cosmic microwave background shows almost no large-scale curvature. But that might just be our local patch. If the whole cosmos is a four-dimensional sphere, unimaginably large, then our tiny slice would naturally seem flat. It's a matter of scale. We're like ants on a giant beach ball. We think the world is a flat plane stretching forever, because we can't perceive the gentle, all-encompassing curve. A universe born inside a black hole tends toward this closed geometry. The intense, focused gravity at the moment of the bounce imparts a specific shape. It creates a cosmos that is finite but unbounded. There's no edge to fall off. If you traveled in one direction long enough after eons, you'd return to your starting point from the opposite direction. But here's the connection. What defines the size of this closed universe? Its maximum scale is set by the original event horizon. The horizon isn't a place in space. It's a moment in the past, the Big Bang, so the boundary of our reality isn't a wall in the distance. It's the beginning of time itself. We aren't looking out at the walls of our prison. We're looking back at them. Every telescope, when it peers at the most ancient light, is staring directly at the interior surface of that primordial event horizon. Stretched and cooled now into the cosmic microwave background, the horizon has been expanding with the universe ever since, but its imprint, its original geometry, is baked into the fabric of everything. So the ultimate sleight of hand is this. We mistake our origin for our limit. We call it the beginning of time when it might also be the boundary of something else. A boundary we can never cross, not because it's far away, but because it is our own past. That oldest light, the cosmic microwave background, it's this faint, cold glow everywhere you look. The afterimage of the universe's first visible moment, a snapshot from when it was just 380,000 years old, a baby picture, but the details in it are fading. And some of them don't quite make sense. The most striking thing is its sameness. The temperature is almost perfectly uniform to an astonishing degree. And that creates a puzzle. Think of two opposite sides of the sky. In the early universe, those regions were so far apart that light couldn't have traveled from one to the other. They were out of touch, causally disconnected. So how did they agree to be the exact same temperature? It's like two people on opposite sides of a continent, with no communication, deciding to wear the exact same outfit. The leading answer is cosmic inflation, a moment of unimaginably fast expansion, faster than light, that happened before the Big Bang we know. It smoothed everything out. It's an elegant solution, but it's not the only one. If our universe was born inside a black hole, that uniformity takes on a different meaning. It isn't a mystery to be solved. It could be an inheritance, a starting condition. Picture the moment of formation. All the matter and energy that would become our cosmos was compressed within the event horizon of that parent black hole. It was a single, unified system, a bounded region. From the very first instant, everything inside that boundary shared a common origin, a common history. The sameness was baked in from the start. The event horizon acted like the walls of an oven, letting everything within reach a uniform state before the great expansion began. So the smoothness might not be a puzzle. It might be a signature, a birthmark, the glow of the horizon itself, stretched and cooled across 14 billion years. But the story gets deeper. The background light isn't perfectly smooth. It has tiny ripples, fleeting variations in temperature, mere millionths of a degree. These ripples are the seeds of all structure. The galaxies, the clusters, the cosmic web. They're the blueprint for everything. In the standard story, these ripples are quantum fluctuations. Tiny random jitters in spacetime during inflation, blown up to cosmic size. They should be random, a Gaussian pattern. But what if they're not entirely random? If our cosmos is the interior of a black hole, then the initial conditions weren't born from pure quantum chance. They were imprinted by the final moments of the star that collapsed. By the structure of the parent universe itself, the chaotic swirl of matter falling in, the magnetic fields, the gravitational waves from the cataclysm. All of that information could have been transferred, scrambled, and imprinted onto the newborn cosmos. The subtle patterns in the cosmic microwave background, the specific arrangements of hot and cold spots, could carry an encrypted message. A fossilized echo of a reality that existed before ours. Scientists have scoured this data for anomalies, for signs of a preferred direction, or patterns that defy pure randomness. And some curious features have been found. A so-called axis of evil, where large-scale patterns seem oddly aligned. A cold spot that's larger and colder than the models predict. Are these just statistical flukes? Or are they the faint, weathered fingerprints of an external world, pressed into the first light of our own? It transforms the cosmic microwave background. From a simple relic into a potential Rosetta Stone. A message in a bottle, cast into the sea of time from a shore we can never visit. Every map we make of this ancient light is not just a picture of our infancy. It is a window, however smudged and distant, to whatever lies beyond the ultimate horizon of our existence. Time just goes one way. That's not just a feeling, it's built into everything. We remember the past, not the future. A cup breaks and the pieces don't jump back together. That's the arrow of time. It only points forward. But in physics, the equations are often symmetrical. The laws work backward just as well as forward. So why does our experience have this one-way flow? The answer might be in the walls of our cosmic room. Think about a black hole. At the event horizon, space and time swap roles. Outside, you move through space, but time pulls you forward. Inside, the direction to the center. What was space becomes your future. Every path leads inward. No stopping, no turning back. Time there has a clear direction, toward the singularity. Now take that logic to our universe if it formed inside such a horizon. The Big Bang wouldn't just be an event in our past. It would be the central point, the singularity that all time is flowing toward. We're not moving away from it in time. We're falling toward it. Our whole cosmic history from the first light to now is that journey along an inward path. The arrow of time isn't some extra mystery. It's the geometry of the universe. It's the shape of our container that ties two big mysteries together. The psychological arrow, why we remember the past, and the thermodynamic arrow, why disorder always increases. They both come from this same cosmic geometry. Right after the Big Bang, the universe was in a state of incredibly low entropy, highly ordered, uniform. That's the starting condition set by the horizon. As the universe expands and we fall forward in time away from that ordered start, entropy naturally increases. Things get more disordered, more mixed. That's why you can scramble an egg but never unscramble it. The process only goes one way because the whole cosmos is sliding down a one-way slope toward its future center. Our perception of time's flow isn't an illusion. It's a direct physical experience. It's the sensation of living inside a gravitational well so vast we think it's all of existence. We feel time moving forward because every atom, every photon, every thought is carried along by the deep, structural current of space itself, flowing inward toward a destination we call the past. The past isn't behind us, it's the center we're all approaching. The future is the path that leads there, that turns our intuition inside out. We think we're looking back toward the Big Bang. But in this view, we're actually looking toward our ultimate future. The whole story of the cosmos, from galaxies forming to stars dying, is the unfolding narrative of that long, slow fall. Our prison doesn't have bars, it has a clock. And the ticking of that clock is the expansion of the universe, the cooling of stars, and the beating of every heart, all moving in step toward a single, inescapable point. The arrow of time points toward a future that looks like the past. It's a cosmic paradox. It reshapes our place in the story, but our origins might be written in the sky, and also in the particles that make up our world. There's a ghost in the machine of particle physics, a particle that should exist but has never been found. It's called a magnetic monopole. Think of every magnet you've ever held. It always has two poles, a north and a south. Break it in half and you get two smaller magnets, each with its own north and south. This duality seems fundamental. A rule, yet our best theories of the early universe insist it must have been broken. In the first moments, the heat was unimaginable. The forces of nature were unified. And when those forces broke apart like water freezing into ice, the theory predicts defects, cracks in reality. These cracks would be particles with a single magnetic pole. A north without a south. Massive, stable relics. They should be as common as protons. They should be everywhere. We have looked deep in mine shafts, in particle accelerators, in ancient minerals that have recorded cosmic rays for millions of years. The result is silence, absolute silence. Not one has ever been detected. Their absence is profound. It's a crisis for the standard story. The most popular solution is cosmic inflation again, that brief period of hyper-expansion. It would have stretched space so thin that any monopoles formed would be diluted to effectively zero in our observable patch. They are out there, the theory says, but so impossibly far apart we will never find one. But there is another solution. One that writes the monopole problem into the architecture of our cosmic room. Consider the conditions of our hypothetical birth. If our universe was born inside a black hole, it was likely not just any black hole, a rotating one. A Kerr black hole. The physics inside such an object isn't just about crushing density. It's about extreme torsion, a twisting of spacetime itself. This rotational environment could have a critical effect. It might suppress the phase transition, the one that creates those cracks in reality. The forces might have separated more smoothly, without the violent ruptures that spawn monopoles. In this view, the missing monopoles aren't a problem to be solved by inflation. They are a signature, a quiet fingerprint, left by the unique physics of our cosmic womb. The absence of these particles isn't an accident of dilution. It's a direct consequence of how our universe began, within the whirling, twisted geometry of an event horizon. It means our most powerful particle colliders, like the Large Hadron Collider, are searching for more than the building blocks of matter. They are, in a way, conducting an archaeological dig. Every high-energy collision is an attempt to recreate the conditions of the early universe, and in that search, the things we do not find are just as telling as the things we do. The continued, profound absence of the magnetic monopole is a silent shout from the beginning of time, a shout that says the rules here were set somewhere else. Under a different sky, in a reality where magnets might have been born with only one face. The monopole's silence, it's a clue in negative space, but there's a concept that pushes this idea of encoded information to an extreme. It suggests our whole reality could be a kind of grand illusion. Think of a hologram on a credit card. It looks like a 3D eagle floating there, but that image isn't truly three-dimensional. It's a flat, two-dimensional surface covered in microscopic grooves. When light hits it right, your brain gets tricked. You see depth and solidity where there isn't any. The information for the whole 3D scene is stored entirely on that 2D sticker. The holographic principle in physics proposes something like that for the universe. It came out of trying to solve the black hole information paradox, and the math showed something startling. All the information needed to describe everything inside a region of space, every star, every atom, every thought, could be perfectly encoded on the surface area surrounding that region. Not in its volume, but on its skin. The interior, with all its 3D complexity, would be a projection, a cosmic hologram. Now take our cosmic room. If our universe exists inside a black hole, then its boundary is the event horizon. That spherical surface, stretched to cosmic size by 14 billion years of expansion, becomes the ultimate hard drive. The cosmic microwave background we see might be more than ancient light. It could be the active projection screen. The data in its temperature variations and polarization patterns wouldn't just be a snapshot of the early universe. It would be the source code for the universe itself, playing out in real time. Your perception of depth, of solidity, of moving through a 3D world, would be the result of this immense, ongoing projection. The galaxy Andromeda, 2.5 million light-years away, isn't out there in a traditional sense. It's a pattern of information on the boundary being rendered for you right here and now. The chair you sit on, the device you hold, even the electrical signals that form your consciousness, all of it is part of the holographic movie. A movie whose projector is the laws of physics, and whose screen is the very edge of reality. This isn't speculative philosophy. It's a rigorous framework in string theory and quantum gravity, even if it's deeply counterintuitive. The mathematics finds a natural home in a universe with a definite boundary. A universe like one born inside an event horizon. The implication is humbling and also liberating. We aren't separate entities moving through an objective external space. We are dynamic patterns in a unified field of information. The separation between you and the distant stars is an illusion of the projection. At the fundamental level, everything is interconnected, because everything shares the same source code on the same cosmic surface. It means the search for a theory of everything might not be a search for the particles at the bottom of the box. It might be a search for the rules of the projector. The laws that govern how two-dimensional information on the boundary translates into the three-dimensional world of our experience. Our entire reality, in this view, is a magnificent shadow play. A story written on the walls of our cosmic room, and then brought to life in breathtaking detail for an audience that is, itself, part of the show. The holographic universe is a story written on the walls. But a story needs energy to unfold. In the late 90s, astronomers found something. They found the universe isn't just expanding, the expansion is speeding up. Something is pushing the galaxies apart. That something is called dark energy. It's the dominant force in the cosmos. It makes up about 70% of everything. And we don't know what it is. In the standard model, dark energy is a placeholder. It could be a constant energy in the fabric of space, or it could be a new field. Its nature is the biggest unsolved puzzle. Now, step into the black hole universe. What if this push isn't from a new substance at all? What if it's a symptom of where we are? A geometric effect of living inside an event horizon. Recall the strange flip. Inside a black hole, the direction to the center becomes your future. Everything is falling inward. But from our perspective inside, that inward fall isn't experienced as a collapse. The universe is expanding. The key is how we perceive that motion relative to the boundary. Think of it like this. You're in a vast, inflating balloon. The surface of the balloon is the event horizon stretching. You are not on the surface. You are inside the balloon's volume. As the balloon inflates, every point inside moves away from every other point. That's the expansion we measure. But the driving force could be the dynamics of the balloon's skin itself. Its relentless outward push against nothingness. In the black hole model, the accelerated expansion might be an intrinsic feature, a consequence of the interior geometry evolving in time. As the universe ages, as we continue our long fall toward the central future, the mathematics of this curved space can produce an effective repulsive force. It looks like a mysterious energy, but it's just the shape of our room changing. This turns the problem on its head. For decades, we've searched for dark energy in the void between galaxies. We've built telescopes to map its effects, but we might have been looking in the wrong place. The answer may not be a new particle or field. It might be written into the cosmic address of our universe. A universe with a boundary naturally wants to accelerate its own expansion as it evolves. The riddle of dark energy becomes a clue. Its apparent strength, its dominance in this cosmic era, could be a direct measurement. A measurement of how far we've fallen from the horizon toward the center. The acceleration isn't a mystery to be solved with new physics. It's a clock. A vast, cosmic clock telling us where we are in the story of our confined existence. Solving it won't require a bigger collider. It requires a shift in perspective. A willingness to see the push not as something in space, but as the signature of space itself, shaped by the walls we can never see. The deepest way out of a singularity isn't a bounce. It's a spin. The black holes we actually see aren't still. They come from stars that were spinning, and that spin gets carried over, amplified to an extreme. These aren't the simple black holes from the diagrams. They're Kerr black holes, and their insides aren't dead ends. They're gateways. In a rotating Kerr hole, that point of infinite density gets replaced. It becomes a ring singularity, a loop of material unimaginably dense, spinning so fast that centrifugal force keeps it from collapsing to a point. And this ring sits inside a structure of horizons. There's the outer event horizon, the point of no return. But inside that, there's another boundary, an inner Cauchy horizon. If you cross this inner horizon, the theory says something changes. The gravitational pull reverses. Instead of being crushed, you'd find repulsive gravity, a tunnel that changes the whole idea of our cosmic room. If our universe was born inside a Kerr black hole, the story doesn't end with a central crush. The matter that became our Big Bang might have passed through that spinning ring. It might have avoided the singularity completely, emerging into a new region of spacetime. Our entire cosmos could be one chamber in a vast complex, a room with a passageway. That passageway has a name from Einstein's equations, an Einstein-Rosen bridge. We call them wormholes. The ring singularity of a Kerr black hole could connect mathematically to the ring of a white hole in another universe, a white hole being a theoretical point where matter erupts outward. So our universe, in this view, isn't a solitary bubble. It's a node in a cosmic network, a multiverse not of separate realms but of tunnels and bridges. All born from the spinning hearts of black holes in parent universes. This rotation wouldn't just be a footnote. it would have left a mark on us. A spinning black hole has a preferred axis, a cosmic north and south defined by its spin. If our universe inherited that spin, then the whole cosmos might have a subtle handedness, a preferred direction imprinted on the largest structures. Scientists have looked for this. They've studied the rotations of hundreds of thousands of galaxies, searching for signs their spins align along a cosmic axis. Some studies have reported large-scale correlations, hints of a vast, swirling pattern across the sky. The cosmic microwave background has been scrutinized too, for asymmetries that could point to a primordial spin. The evidence isn't conclusive. It could be noise, but the search is telling. We are trying to read the compass of our parent black hole in the arrangement of galaxies. The spin imprints more than direction. It imparts torsion, a twisting of spacetime itself. This could have influenced the fundamental forces as they froze out early on. It might explain other mysteries like the dominance of matter over antimatter. The very handedness of life, the chirality of molecules, could trace back to that initial, defining rotation. So we're left with a possibility. Our universe may not be an island, it may be a corridor. The accelerating expansion we measure, the arrow of time we feel, the three-dimensional reality we experience, could all be the local conditions of this particular chamber. And through the ring at its heart, a heart we call the Big Bang, there might lie a passage to another realm. We aren't just living inside a black hole. We might be living inside one doorway of an infinite, spinning labyrinth. Gravitational waves are these ripples in spacetime. They come from the most violent events. Two black holes colliding billions of years ago sends out a tremor. We can feel that tremor now. It's like hearing the universe's deepest notes. But if our universe is a room, these waves are the sounds we make inside it. So you have to ask, can we hear sounds from outside? The event horizon is a one-way barrier, by definition. Not even light can escape inward to tell us what's happening out there. So a direct signal, a clean gravitational wave from a merger in the parent cosmos, it likely can't cross into here. The horizon isn't a drumhead. It doesn't vibrate freely both ways. It's more like a waterfall's surface. It absorbs whatever falls over it. But think of a massive impact on the other side of a thick wall. You wouldn't hear the shout. But you could feel the wall shudder. A truly colossal event out there, the formation of a supermassive black hole, galaxies colliding. That wouldn't be a gentle tap. It would be a quake. An event like that deposits immense energy directly into the event horizon's structure. It distorts it, vibrates it in a fundamental way. And that distortion, that shudder of the boundary, would propagate inward, into our cosmos. It becomes part of our universe's initial conditions. The imprint would be subtle, woven into the geometry of space from the very first moment. So we can't listen for a specific event's chirp from outside. But we might find the fossilized vibrations it left behind. These would show up as specific patterns in the oldest light we see, the cosmic microwave background, or more tantalizingly, in the gravitational wave background. That faint, constant hum from all the mergers throughout history. Current observatories like LIGO and Virgo, they listen for individual, loud events. But the next generation, like the planned LISA observatory in space, it will be tuned to hear this background hum. Scientists will map it with incredible precision. And in that map, they'll look for anomalies, patterns that don't fit the expected chorus of mergers from within our own universe, an all-sky correlation. A preferred direction or frequency in the hum with no internal source. A discovery like that would be profound. It would be like hearing a knock on the walls of our reality. A faint, rhythmic pulse encoded in the fabric of space. A remnant of a shockwave that traveled across the boundary when our universe was created. A message not in light, but in the twisting of space-time itself. A signature that the room we're in isn't perfectly insulated. That its walls, though impenetrable, once trembled from a force beyond us. The search isn't for a clear signal. It's for a ghost in the data. a whisper of outside causality pressed into the first vibrations of everything. Every new gravitational wave we detect from within brings us closer to a complete map of our internal cosmos. And in the quiet spaces between those detections, in the subtle statistics of the hum, we might one day find evidence that our story is just one chapter in a much, much larger book. Our search for a knock on the wall just leads to the deepest silence there is, the silence of the cosmos. Enrico Fermi asked this question decades ago. Given how old the universe is, how big it is, with all those billions of stars and planets, where is everybody? If life is common, the galaxy should be full of it. We should see signs, we should hear signals, but we don't. We hear nothing but static. That's the Fermi paradox, and there are a lot of solutions. Maybe civilizations are rare. Maybe they destroy themselves, or maybe they're just too far away. But our idea offers a different answer, a more profound one. It doesn't need a cosmic graveyard. It needs a cosmic room. If our universe is inside a black hole, then the event horizon isn't just a boundary of space and time. It's the ultimate communication barrier. A one-way filter for information. Light, radio waves, gravitational waves, any signal from a civilization out there, in the parent universe, can't cross in. The laws of physics forbid it. To them, our cosmos is a sealed vault. And from our perspective, the entire external universe is a moment locked in our past. We aren't just distant from other stars, we're ontologically separate. We exist in a different chapter of reality, and you can't turn those pages backward. That isolation could solve the paradox in a single stroke. We aren't hearing from aliens not because they don't exist, but because we're fundamentally disconnected. We're in cosmic quarantine. So the great silence isn't a sign of emptiness. It could be the signature of our confinement. The static on our radio telescopes isn't just the hiss of dead stars. It's the sound of a locked door, but the implications go further. The conditions inside a black hole, while extreme, might create a uniquely stable environment for life as we know it. The expansion from a hot, dense state, the specific mix of forces, the arrow of time, these aren't universal defaults. They're the local conditions of our particular room. In the vast multiverse of black hole interiors, most might be too chaotic, too short-lived, or too hostile for any complex structure to form. Our universe, with its precise constants and long, cool expansion, could be a rare bubble. A habitable oasis in a desert of cosmic firewalls and rapid collapses. So the answer to Fermi's question might be layered. First, we are alone in here because signals from out there cannot reach us. And second, we might be here at all because this is one of the few rooms where the conditions allowed for someone to ask the question. We're not just prisoners in a cosmic room. We might be the lucky ones who found a room with a window that lets in starlight and air we can breathe. This reframes our entire search for extraterrestrial intelligence. Our efforts to listen for signals, to scan exoplanet atmospheres for biosignatures, those are searches within our room, and they are vital. There could be other civilizations that formed alongside us, from the same primordial soup, sharing the same bounded reality. They would be our true cosmic neighbors. But the dream of contacting a civilization from another universe, a parent reality, is likely forever out of reach. Not due to distance, but due to the fundamental architecture of existence. The silence, then, is not empty, it's full of meaning. It's the quiet hum of a self-contained system. A reminder that every question we ask about the cosmos is also a question about the nature of our own home. And if our home has walls, then some messages, no matter how loudly sent, are never meant to arrive. The silence in a room can be deep, but the walls that make that silence might be made from the most basic stuff of reality. At the center of a black hole, there's a singularity. That's where Einstein's math for gravity breaks down. The gravity becomes infinite. Space and time, our understanding of them, it just stops. This isn't really the theory failing. It's more like a sign that points to something deeper, where gravity has to meet the quantum world. If our Big Bang started from a point like that, or from a quantum bounce that avoids it, then the first moments weren't just hot and dense. They were the ultimate test for quantum gravity, the place where the rules of reality were being written. The black hole universe model gives that idea a place to live. It gives you a real, physical setting, a place where the most extreme ideas from quantum gravity theories would have played out, on a cosmic stage. Theories like loop quantum gravity or string theory try to describe this. They say spacetime isn't a smooth, continuous fabric. At the smallest scale you can imagine, much smaller than a proton, it might be grainy, like a tapestry woven from separate, quantum threads. In today's calm universe, that graininess is invisible. But in the furious energy of the beginning, dictated by the quantum properties inside that parent black hole, this basic graininess could have left a mark. Think of the universe in its first instance. Space is expanding faster than light. But if space-time is granular, that expansion might not have been perfectly smooth. It could have had a little jitter, like a film projected with a shaky reel. That quantum jitter, stamped onto the fabric of everything, would have been stretched across the whole cosmos as it inflated. It would become a permanent part of the background of reality. So how do you look for the fingerprints of quantum gravity? You search for its echoes. In the oldest light and the most energetic particles, the cosmic microwave background, that baby picture of the universe, is one place. Its polarization, the specific direction its light waves vibrate, could carry faint, swirling patterns. They are called B modes, generated by gravitational waves from the quantum era. Detecting a specific signature in those patterns could be a direct message. From the moment quantum gravity ruled, another window might be the most powerful particles, ultra-high-energy cosmic rays. These are single protons or atomic nuclei, hurtling through space with energies millions of times greater than anything our biggest colliders can make. Where they come from is a mystery, but some theories suggest that if spacetime has a granular structure, these ultra-high-energy travelers might be subtly affected by it. Over billions of light years, they might arrive at Earth with a characteristic signature, a tiny anomaly in their behavior that shows the bumpy road they traveled. Finding evidence like that would change everything. It would mean the largest structures we see, galaxies, clusters, the cosmic web, they all trace back to the quantum fuzz of spacetime. At the smallest possible scale, the black hole universe idea makes this connection solid. It says the conditions that started our reality weren't generic. They were the specific, quantum gravitational conditions inside an event horizon. The granularity we might detect isn't just a math problem. It's the fossilized texture of our cosmic womb. We usually think of quantum effects as fragile, confined to tiny particles in labs, but this possibility flips that around. It suggests quantum gravity isn't hidden from us. Its signature might be written across the entire sky, waiting in data we've already collected. We just have to learn how to read it. The search for quantum gravity becomes like an archaeological dig into our own origin story, using telescopes and particle detectors as tools to uncover the first brushstrokes on the canvas of existence. Our existence as a material world is a kind of cosmic accident. You look at your hand, the chair, the stars, it's all matter. But physics says the Big Bang should have made equal parts matter and antimatter, and when they meet, they annihilate. Pure energy, if it had been perfectly balanced, everything would have cancelled out. The cosmos would just be light, empty, sterile, but that's not what happened. We're here, the universe is full of stuff. Galaxies, planets, us, that's the Baryon asymmetry. It's one of the deepest puzzles. Why does matter dominate? The Standard Model, our rulebook for particles, has processes that can create a slight preference for matter. But the preference it allows is tiny, far too small. By many orders of magnitude, it can't explain the overwhelming sea of matter we see. So something else had to tip the scales, something powerful at the very beginning. And that something might be written into the walls of this room. Consider the moment of our origin. A massive, rotating star in a parent universe reaches the end. Its core collapses, and this isn't gentle, it's violent. Chaotic, magnetic fields wound to unbelievable strengths. Neutrinos trapped, flooding out. Spacetime itself twisted by the star's spin. In that maelstrom, conditions are ripe for violating a fundamental symmetry. CP symmetry, which says the laws of physics should treat matter and antimatter as perfect mirrors. But in that collapsing star, the mirror can shatter. Processes that favor matter over antimatter could operate on a colossal scale. The asymmetric collapse, the torsion of spacetime, the sheer violence, all of it could imprint a bias. A preference for one particle over its opposite. Now, if our universe was born from the quantum rebound inside that event horizon, it inherited everything within that boundary. It inherited that overwhelming bias. So the fireball of our Big Bang didn't start balanced. It started with a legacy, a preloaded preference for matter, baked in from the catastrophe that created the room. In this view, every atom in us isn't just stardust. It's fallout from a cosmic battle in another reality. The antimatter that should be here was mostly filtered out, annihilated in the first instance, leaving behind the excess matter as the raw material for everything. We aren't here despite the laws of physics. We're here because of a specific, violent exception to those laws. An exception that happened in the most extreme laboratory imaginable, the heart of a dying star as it forged a new reality. And that transforms the Baryon asymmetry from an abstract puzzle into a personal story. The reason you're made of matter and not antimatter might be because a star died in a particular, lopsided way, in a universe you can never see. Our material world isn't the default state. It's a fossil, a relic of a singular, asymmetric catastrophe, preserved forever in the expanding echo of its own creation. The cosmos is huge. That's the first thing you notice. Billions of galaxies, each with billions of stars. Distances so big that light takes billions of years to cross them. It feels infinite. That feeling of boundlessness, it might be the universe's best trick. We measure it. The observable universe is about 93 billion light-years across. A staggering volume. To think all of that could be inside something, inside a black hole, seems impossible. A black hole is a point, a vacuum cleaner. How could it hold a universe? The answer is gravity, a kind of cosmic sleight of hand. From the outside, a black hole has a boundary, the Schwarzschild radius. It's based on mass. For a black hole with the mass of our universe, that radius would be enormous. Tens of billions of light-years, but that's the radius from the outside. That's the width of the doorway. Inside, it's different. The gravity at the moment of creation stretches space. Imagine a sheet of rubber. You see a small circle drawn on top. That's the Schwarzschild radius. Now push that circle inward with incredible force. Create a deep, funnel-shaped well. The surface area of that funnel from the inside is much larger than the original circle. You've created more space within the boundary. That's the geometry inside a black hole. The space within the event horizon isn't flat. It's profoundly curved. In that curved geometry, distances aren't what they seem. A journey from the horizon to the central point. What would become our Big Bang isn't short. It's a path through an expanding landscape. The volume inside can be far, far greater than any outside calculation would suggest. A universe-sized black hole could have an interior so vast its inhabitants would never perceive the edges. The curvature across our local region would be gentle. Space would appear flat, like the Earth feels flat underfoot. The horizon isn't a nearby wall. It's a boundary in the past, a moment in time. We aren't looking out at it from the center. We are within it and it expands with us. That solves the scale problem. We aren't in a tiny, cramped cell. We're in a cosmic cathedral. Its architecture creates the perfect illusion of infinity. The walls are so distant, set in a dimension we experience as time, that they define our reality without limiting it. The universe feels open and endless because, from our vantage point inside its geometry, it genuinely is. Every telescope peering deeper into space, revealing more galaxies at the edge of our vision, isn't approaching a limit. It's tracing the curved surface of our confinement. The darkness between the stars isn't empty space waiting to be filled. It's the shape of the room itself, stretching on in a beautiful, boundless illusion. Our home is finite and without edges, a closed cosmos that feels infinite because its only boundary is the beginning of everything. A theory that works doesn't just explain things. It makes predictions. It tells you where to look for this idea that we're inside a black hole. The evidence wouldn't be one big discovery. It would be a pattern, a set of clues woven into the universe itself. So we need to know where to look and what to look for. The first clue is the shape of space, the geometry of everything. Is it flat or open or closed? Our best measurements from the cosmic microwave background say it's incredibly flat. But there's a small uncertainty. The data allows for a slight positive curvature. And a universe with positive curvature is a closed sphere, finite with no edges. That's exactly the geometry you'd expect for a universe born inside a black hole. The next generation of telescopes, like the Euclid mission, are built to measure this curvature with much more precision. If they find even a hint of positive curvature, it would change everything. It wouldn't prove the idea, but it would open the door. It would mean our cosmos has a definite shape, a room with walls. The second clue is in the oldest light. The cosmic microwave background. We've talked about its patterns, but scientists are looking for specific anomalies. One prediction is concentric circles, ripples inside ripples. These could be imprints of violent events that happened before our Big Bang in a parent universe. They're gravitational waves echoing onto our new sky. Another signature is called non-Gaussianity. The temperature variations in the CMB are mostly random, like static. But if they contain specific, non-random patterns, certain statistical shape, it could mean our universe didn't start from a perfectly smooth quantum state. It could mean it inherited structure from a prior cosmic era. Finding these fingerprints would be like finding a watermark on the first page of our history. A watermark from another book. The third thread involves the very first black holes, primordial black holes. These wouldn't form from collapsing stars. They'd come from the dense, churning soup of the early universe. If our cosmos began with a quantum bounce from a parent black hole, then the distribution of these primordial black holes, their masses, their numbers, might carry a statistical signature. A specific pattern that models of such a bounce predict. We haven't found definitive evidence of primordial black holes yet, but they're still a candidate for dark matter. If future observatories like the Vera C. Rubin Observatory detect a population of these ancient objects, their demographics could tell a story about how our room was built. The final test looks at the rules themselves. The fundamental constants, the strength of gravity, the mass of an electron. Why do they have the precise values that allow for stars and planets and life? Cosmological natural selection, the idea that universes evolve, makes a prediction. Universes that produce more black holes have more offspring. So a universe like ours should be tuned, not for life, but for black hole production. We can check this. We can calculate whether the constants we measure are optimal for creating the maximum number of black holes across cosmic history. If they are suspiciously optimized for that purpose and not for our existence, it would be a powerful piece of evidence, a chilling one. It would suggest we are not the point of the story. We're a side effect in a cosmic lineage driven by replication. None of these tests alone would be conclusive. Science rarely gives you a single, blinding moment of proof. Instead, it builds a case, a convergence of evidence. If the geometry is closed, if the CMB carries echoes of a prior reality, if the first black holes are arranged just so, and if the constants seem tuned for cosmic fertility rather than comfort, then the picture becomes harder to ignore. We'd be left with a map of our confinement, drawn in the language of mathematics and written across the sky. The search for these clues is already underway. In the quiet hum of data from telescopes and satellites, We might be slowly reading the address of our cosmic home. The search for clues is scientific. But if the map is confirmed, if the evidence all points the same way, then you're left with a question science can't answer. What does it mean? If our universe is a self-contained room, born from a cataclysm in another reality we can never reach, then everything we know is secondary. A complex accident inside something grander. This isn't just a new fact, it's a philosophical earthquake. For centuries, human thought has often put us at the center. Our stories, our religions, even our sciences, many assumed this cosmos was made for us, that we were its point. This idea shatters that. It suggests we are not the purpose. We are a possibility within it, one outcome of physics playing out in a specific kind of cosmic chamber. The laws here, they aren't necessarily fine-tuned for life. They might be fine-tuned for black hole production. Life could be a rare byproduct. We are not the story. We are a footnote in a story about cosmic reproduction. It challenges narratives of a uniquely created universe, not by disproving them, but by expanding the stage. If universes are born inside black holes, then creation isn't a singular event. It's an ongoing process, a kind of cosmic ecology. Realities live and die and give birth to new realities. Our Big Bang wasn't the beginning of everything. It was a beginning, one link in a chain, so where do we find meaning? The search can't stop at the borders of our spacetime. Purpose might not be written into the local laws for us to find. It might be something we create, something we project onto this vast, indifferent architecture. Our stories, our art, our love, our curiosity, these aren't diminished by a larger context. They become more precious. They are the light we generate inside the room, the only light of its kind. This perspective is humbling, but it's also strangely unifying. It suggests that every star that dies, every black hole that forms, isn't an end. It's a potential beginning. The matter that makes you was forged in stars. But those stars themselves, they might be the grandchildren of a stellar collapse in a forgotten cosmos. You are not just stardust. You are the legacy of an infinite lineage of transformations. A witness to one chapter in an epic that has no author, only process. Our drive to understand, to look up and ask why, it takes on a new character. It's no longer just about mapping our home. It's an attempt to read the blueprints of the room, to infer the nature of the builder from the walls. Every equation, every telescope image is part of a grand detective story, where the ultimate mystery isn't how the universe works. It's why this particular universe exists at all. And the answer, it seems, may point beyond itself, to a silence more profound than we imagined. Our search for meaning goes outward, but the structure of reality might be branching inward. The multiverse feels abstract, something from quantum math or philosophy. But if our universe formed inside a black hole, the multiverse becomes concrete, almost mechanical. It's a family tree written in gravity and stellar death. A star massive enough to collapse into a black hole in a parent cosmos doesn't just vanish. It becomes a seed for a new, self-contained reality. With its own Big Bang, its own expansion, its own history. Each of these daughter universes is sealed off from its parent, and from its siblings. The event horizon is the ultimate isolation chamber. No signal can cross back out. So each new cosmos starts fresh with its own set of rules. The physical constants, the strength of gravity, the mass of an electron might not be universal at all. They could be local variables, set randomly or influenced by the specific conditions of the collapse that birthed them. One black hole might produce a universe where gravity is 10 times stronger, where stars burn out in a cosmic blink. Another might yield a cosmos where the nuclear forces are weaker, preventing atoms from ever forming. Most of these offspring would be stillborn, hostile to any complexity. But sometimes, by sheer chance, a collapse produces a universe with a delicate balance, like ours, capable of forging stars, planets, maybe life. This creates a vast, branching fractal of realities, not side by side like pages in a book, but nested, connected by lineage. Our universe is one branch. The black holes forming within our own cosmos like Sagittarius at the Milky Way's heart are not just endpoints. They are potential gateways. Each one could be the progenitor of a whole new cosmos. Utterly disconnected from our own, with laws we cannot imagine. We are not just living in a universe that came from a black hole. We are living in a universe that is manufacturing the seeds for countless others. This transforms the multiverse from a philosophical idea into a physical prediction. It offers a mechanism, a prolific, natural mechanism for generating cosmic diversity. Driven by the most common catastrophic events in the universe, the death of massive stars, the infinite variety of possible universes isn't a mathematical abstraction. It's the direct result of slight variations. How stars spin, their magnetic fields, their exact composition at the moment of collapse. In this view, our fine-tuned constants are not a miracle. They are a lottery ticket, one of countless tickets drawn in a cosmic game of chance, a game that's been running for eternity. We exist in a universe that could form black holes. And in doing so, continue the cycle. Our reality might be particularly fertile, optimized not for us but for replication. This connects everything. The arrow of time, the accelerated expansion, the matter-dominated world. All of it could be features of a universe built to produce more of itself. Our story is not an end. It's a link in an endless chain. A single leaf on an infinite tree of realities, forever growing in directions we can never see. The universe will end, that much we know, but how it ends, that's still an open question. The main idea is heat death, a slow fade. Expansion just keeps going, galaxies pull apart, stars go dark, and you're left with this vast, almost empty space. Just scattered particles. Entropy wins, everything goes still. Another possibility is the Big Rip. If dark energy gets stronger over time, it could eventually tear everything apart. Galaxies first, then stars, planets, down to atoms themselves. A violent unraveling, then there's the big crunch. The expansion slows, stops, reverses. The universe collapses back in on itself. Ends in a fiery singularity. Those are the standard endings. But if our universe is like a room, its fate isn't separate. It's tied to whatever contains it. Tied to the fate of the black hole. From inside, we measure expansion. We see galaxies moving away. We feel dark energy pushing. That could just be our experience of the interior geometry changing. But from an outside view, if there was one, our whole cosmos is just what's inside that black hole. And black holes, according to Stephen Hawking, don't last forever. They evaporate. Over timescales so huge they make the current age of our universe seem tiny. A black hole loses mass. It gives off Hawking radiation, shrinks slowly, until in theory it just vanishes. So what happens to the universe inside when that happens? When the walls of the room evaporate, one possibility is the simplest and the most unsettling. It just stops existing. The structure goes and the projection fades. The hologram turns off. In that view, our whole cosmic story, for all its scale, has an expiration date set by a clock we can't see. The ultimate fate would be an erasure from the outside, while from inside we might experience it as the universe reaching some final, cold, thin state before blinking out completely. But there's another possibility, more cyclical. Some quantum gravity models suggest the interior universe might not be passive. It could reach a maximum size, a point set by the original horizon's properties, and then start to contract. Not just from gravity, but from the interplay between the interior geometry and the fate of the horizon itself. That contraction could lead to a bounce. Another Big Bang. A new universe born from the old one, all inside the same black hole. That gives you a vision of perpetual recycling. Not just a multiverse of separate branches, but a universe that goes through its own cycles. Birth, expansion, contraction, rebirth. A phoenix cosmos. Each cycle could have slightly different constants, different matter, a different history. Life, if it emerged in one cycle, might not emerge in the next. We'd be a chapter in a book that's constantly being rewritten. The evaporation of the parent black hole from the outside might correspond, from our inside perspective, to the completion of one of these grand cycles. The moment of final contraction and bounce, the black hole doesn't vanish, it transforms, it gives birth to a new iteration from within. This reframes how we look for the universe's fate. We look for the strength of dark energy, the curvature of space, the density of matter. Those are clues to the internal dynamics. But the real driver, the reason for the cycle, might be written in the quantum mechanics of the event horizon. A process we're living through, but can only see from the shadows it casts. Our end, then, might not be an end at all. It could be a return to the start, a reset. The great silence of heat death or the violent rupture of a big rip might just be way stations. Points on an infinitely longer journey. We're not just passengers in a cosmos heading toward a final stop. We might be inside a cosmic engine, turning over once every trillion eons, forever making new possibilities from the collapse of the old. The stories about the sky are older than science. Long before telescopes, before equations, people looked up and tried to explain how the world began. And in those old myths, you hear something familiar. Across different places and times, creation stories often start with a point, a seed, an egg, a single contained potential, and then everything unfurls from that. The ancient Norse talked about the beginning. They spoke of Ginnungagap, a yawning, primordial void, a chasm of silence and emptiness, and from that nothingness, the first sparks of a world emerged. In Hindu cosmology, the universe is born from a cosmic egg, the Brahmanda. It emerges from a singularity, a single point of infinite potential, and then it expands outward. It contains all of existence within its shell. The ancient Greeks had the cosmic egg, too. So did cultures from Egypt to China. These aren't just random metaphors. They are a profound human intuition. An intuition that everything we see, the stars, the land, ourselves, didn't just appear in an endless void. It came from somewhere. It hatched. It unfolded from a specific, enclosed origin. Our modern scientific idea that our universe was born inside a black hole feels like a direct descendant of those old stories. It's the same fundamental question, asked with a new vocabulary. Where did the room come from? The myths answered with gods and chaos. Science answers with gravity and quantum physics. But the core shape of the answer is similar. A singularity, a boundary, an interior reality born from a cataclysm in a larger, unseen beyond. This resonance isn't proof. It's a pattern in human thought. It speaks to a deep-seated curiosity, a need to understand our place within a structure. The idea of an enclosed cosmos, a finite creation, feels instinctive. It provides a narrative container, a beginning and potentially an end. The infinite, eternal universe of some classical philosophies feels abstract and cold. But a universe with an origin point, a cosmic womb that feels like a story we can understand. It mirrors our own lives. We are born from a specific event, we grow within a world, and we look back to find our source. So when we use mathematics to describe a quantum bounce inside an event horizon, we're participating in the oldest human tradition. We're myth-making with the tools of our time. The equations of general relativity that describe a singularity are our version of the cosmic egg. The event horizon is our Ginnungagap, the ultimate boundary between the manifest and the unmanifest. This perspective softens the potential loneliness of the idea. If we are in a room, it's a room our species has instinctively imagined for thousands of years. Our drive to find the walls isn't just scientific curiosity. It's the continuation of a sacred, ancient question. By searching the cosmic microwave background for the imprint of a parent universe, we are, in a real sense, trying to read the inscription on the inside of the eggshell. We're using the precision of science to listen for the whispers of the void our ancestors sensed in their bones. The story hasn't changed, only the language we use to tell it. The simulation idea is a modern myth. Nick Bostrom, the philosopher, put it as a logical argument. If a civilization ever got to a point where it could run these vast, detailed simulations of conscious beings, then the number of simulated minds would just completely outnumber the real ones. Statistically, we're more likely to be one of the simulated ones. It's a haunting thought. It means our reality, with all its texture and depth, could be a sophisticated illusion. A program running on some unfathomable computer. But then you have to ask, where would that computer even exist, and who would be the programmer? The holographic black hole universe gives a startling answer. It doesn't need a hyper-advanced alien civilization. It doesn't need a programmer at all. Instead, it says the universe itself is the computer, and the hardware is the event horizon. Think of that horizon again, that spherical boundary. The holographic principle says it's a two-dimensional surface that encodes all the information for the three-dimensional volume inside it. Every star, every planet, every thought you have is described by bits of information on that surface. But information isn't static. It's processed, it changes. The universe evolves. Galaxies collide, stars are born, you make a decision. For the interior reality to change, the information on the boundary has to be updated. It has to be computed. This is where the black hole becomes a natural computer. The quantum gravitational laws that govern the event horizon, the dance of spacetime and energy at the smallest scale. They aren't just sitting there. They are dynamic. They are processing. They take the input of everything that ever fell into the black hole, all that encoded information, and they calculate, moment by moment, what the interior projection should look like. The rendering of our three-dimensional world is the output of that calculation. In this view, the laws of physics aren't just rules the universe follows. They are the operating system. The equations of general relativity and quantum mechanics are the algorithms. The immense energy and curvature of the horizon provide the processing power. Our lived experience of cause and effect, of time flowing, is the real-time result of this cosmic computation. It reframes the simulation argument completely. We are not in a simulation built by someone else. We are in a universe that is, by its very physical nature, a self-running simulation. The programmer is the set of fundamental laws that emerged from the quantum gravity of a collapsing star. The code is written into the fabric of reality at its smallest scale. This makes the search for the theory of quantum gravity even more profound. Finding it wouldn't just be a triumph of physics. It would be like discovering the source code of our reality. We'd be reading the programming language of the cosmos, a language that runs not on silicon chips, but on the quantum geometry of spacetime itself. So when you feel the sun on your skin, or see the complexity of a leaf, you're not interacting with a cheap graphical rendering. You are experiencing the rich, computed output of the most powerful natural processor conceivable. A processor whose walls are the beginning of time, and whose fuel is the history of everything that came before. Our reality isn't less real for being computed. It is real because it is being computed continuously by the ultimate machine, the universe we call home. The idea is heavy. Everything we know might be one room in an endless mansion of realities. And you have to ask, does that change anything? Does it change how we live? On the surface, it could lead to despair. Our struggles, our art, our short lives, they could seem vanishingly small. A whisper in an infinite chain of whispers. Our whole history, just one iteration in a cosmic loop that doesn't care. In that light, our efforts might feel meaningless. A temporary pattern in a system that will eventually reset. It's the ultimate scale problem. It makes our own galaxy feel small, but there's another angle. A pivot. It turns confinement into a kind of significance. Think about the rarity. If most offspring universes are stillborn or hostile to life, then a cosmos like ours, one with stars, planets, oceans, minds, is an extraordinary accident. A statistical miracle inside an infinite lottery. And within this rare cosmos, we've emerged. We are the universe, after billions of years, starting to look back at itself. We are the process becoming aware of the process. A cosmic child born in the room, learning to trace the outlines of the walls. This awareness isn't a small thing. It might be the most significant event in this universe's entire history. The matter from a primordial cloud is now organized, and it can ask where it came from. It can feel wonder at the night sky it's part of. It can create beauty. It can seek understanding. In a potentially endless lineage of blind reproduction, our consciousness is a profound departure. A spark of subjective experience in an objective chain. That fosters a deep form of stewardship. We might be the only consciousness this particular universe ever produces. The only witnesses to its grand, silent story. That makes us not insignificant prisoners, but the custodians of meaning for this entire realm. Our curiosity, our science, our art, these aren't just hobbies. They're the universe's only method for appreciating its own existence. Every telescope pointed at the stars, every equation on a page, that's the room learning about itself. It's a noble rebellion, a defiance against the idea that a closed system has to be an ignorant one. Our ethics then expand. They encompass our whole cosmic home. The drive to preserve, to understand, to create these impulses gain a new dimension. We're not just caring for a planet. We're honoring the specific, rare conditions that allowed for a story to be told here at all. The fragility of life on Earth echoes the fragility of a habitable universe. Both are unlikely gifts in a vast silence. So, does it change how we should live? Maybe it asks for a dual awareness, to hold the humbling scale of our possible confinement, alongside the breathtaking rarity of our conscious presence within it. Our actions matter, not because they'll echo through the multiverse, but because they are the only echoes this universe will ever know. We are the authors of meaning in a story that otherwise would have none. That's not a small task. It's the most important task there could be. The question of proof. It means we're looking at a wall we can't see over, because the hypothesis itself puts the most important evidence out of reach. The parent universe, the star that collapsed, the physics that govern that place, those events are causally disconnected from ours. No signal, no light, no gravitational wave from that outside reality can ever cross the one-way barrier of our origin. In a direct, experimental sense that makes the idea seem untestable. It could just float into metaphysics, a beautiful story, but forever beyond verification. That's the ultimate challenge. We're detectives locked inside a room, trying to figure out who built the house using only the furniture inside. We can study the grain of the wood, the style of the craftsmanship, the wear on the floorboards. We can build a compelling, consistent case about the architect's methods, but we can never step outside to check the property records. The direct witness is gone. And yet, that doesn't make the investigation meaningless. The indirect evidence can be profound. The shape of space, the patterns in the ancient light, the absence of certain particles, the arrow of time itself. These are the wear patterns on the floorboards. If a confluence of these internal signatures all points toward a single, coherent narrative of a bounded origin, the case becomes powerful. It would be a circumstantial case, but of breathtaking scope. We wouldn't have a photograph of the parent star, but we might have its fingerprint, smudged across the entire sky. It's a beautiful and deeply frustrating truth about cosmology. We're trying to understand the container from within, using only the clues embedded in the container itself. Every measurement, every observation is part of a closed loop. Our greatest theories are maps we draw of the room, and we check their accuracy by comparing them to other maps we've made from slightly different vantage points inside the same room. The quest for absolute external confirmation may be logically impossible, but that very limitation expands the horizons of thought. It pushes science to its philosophical edges. It demands new kinds of questions. Instead of asking for a direct signal from outside, we learn to ask what the signature of an outside would look like, translated into the internal language of our physics. The pursuit transforms. It becomes a search for self-consistency on a cosmic scale, a drive to see if the story of our universe makes more sense, if it becomes more elegant and complete, when viewed as a chapter rather than the entire book. The journey to know might be endless. A final, definitive answer may forever hover just beyond the boundary of our cognition. But in the striving, in the meticulous gathering of clues and the bold interpretation of shadows, we do something remarkable. We turn the limits of our knowledge into the very engine of discovery. We may never know for sure if we live inside a black hole, but the possibility alone has already reshaped how we see our place in the dark. The most successful scientific theory isn't just a story we like. It's the one that fits the evidence. For cosmic origins, that story for decades has been cosmic inflation. It's the reigning champion, and it solves real puzzles. The universe is incredibly uniform. The geometry of space is remarkably flat. Inflation explains both at once. It says that a fraction of a second after the initial moment, space-time underwent a brief exponential expansion, faster than light, that stretched a tiny, uniform patch into our entire observable universe, ironing it flat in the process. It's a powerful idea, and its predictions for the specific pattern of ripples in the cosmic microwave background have been confirmed with stunning precision. This isn't a fringe concept. It's the bedrock of modern cosmology. So when we consider the black hole universe model, we aren't replacing a weak idea. We're challenging a robust, well-tested framework. The question becomes, can this new story do everything the old one does and maybe something more? The black hole model must either incorporate a version of rapid expansion inside the event horizon, which some versions do, or it must find another way to explain the smoothness and flatness we observe. Maybe that smoothness is an inheritance, a starting condition from the bounded, pre-mixed material within the horizon. The flatness could be a local illusion within a vast, closed cosmos. But these are alternative explanations. They have to be tested with the same rigor. The scientific method thrives on this tension. We don't choose the idea that feels most profound. We weigh them. We ask which framework explains the most with the fewest assumptions. Does the black hole model solve puzzles that inflation leaves untouched? Consider the origin of the arrow of time. Inflation doesn't address it. The nature of the initial singularity. Inflation starts just after that moment, sidestepping it. The potential source for our universe's specific constants. Inflation is largely silent. The black hole model wades directly into these deep waters. It offers a physical mechanism for the beginning, a geometric reason for time's flow, and a potential explanation for why our constants are what they are. But this comes at a cost. It adds layers of complexity. It proposes entities like a parent universe that are inherently unobservable. To some, that feels like a step backward, a retreat from testable science. To others, it feels like a necessary step toward a more complete picture. One that doesn't stop at the moment our physics breaks down, but seeks a physical cause for that moment itself. This debate isn't a weakness. It's the engine of discovery. It forces both sides to sharpen their arguments, to make clearer predictions. The next generation of telescopes won't just collect data. They will act as a jury. Measuring the curvature of space with finer precision could tip the scales. Finding a specific, non-random pattern in the cosmic microwave background that inflation doesn't predict could be a breakthrough. The goal isn't for one story to win and the other to vanish. It's to move closer to truth. Sometimes that means a radical new idea absorbs the best parts of the old one and moves forward. Perhaps our universe did inflate, but that inflation was a phase inside a larger, bounded structure. The real value is in the questions this competition raises. It pushes us to look at the evidence with fresh eyes, to wonder not just how our universe works, but why it is this particular way, in this particular place. The search for our origin is a conversation, not a monologue. And the most interesting chapters are always the ones where we dare to question the prevailing narrative. The equations of quantum mechanics have this strange implication. That observation isn't just looking, it's part of the process. In the double-slit experiment, a particle is a wave of possibilities. Until you measure it, then it picks a spot. The universe seems to need a witness to decide. That's led to a lot of debate. Is it consciousness that collapses the wave function? Or just the physical act of measuring? The question sits there at the edge. Now put that question into a holographic universe, where all the information for our 3D world is stored on a 2D boundary. Our reality is a projection from that data. In a system like that, what is an observation? You look at a star, light hits your eye, signals fire in your brain. That's a physical process, but from the holographic view, it's also an update. To the information on the boundary, your observation becomes an event in the cosmic computation. A request for data from the source code, and the source code responds. It renders the star for you in that moment with a specific history and position. This is speculative, but it opens a possibility. In a self-contained holographic reality, the interior experience and the boundary description are two sides of the same thing. They are equivalent, so collective observation by every conscious being inside might not be a side effect. It could be part of the process, the mechanism that translates the abstract information on the horizon into the concrete, shared reality we experience. Our curiosity, our act of looking and measuring, could be the universe reading its own script aloud. Consciousness, in this view, isn't an accident of chemistry. It becomes a feature of the architecture, a necessary component for the projection to be experienced, and therefore, in a deep sense, to be fully real. The room needs someone in it to give meaning to the walls. This isn't about controlling reality with our thoughts. The source code, the laws of physics on the boundary, sets the rigid rules. But within those rules, observation might be the trigger that selects one specific outcome from a sea of quantum possibilities. It makes every conscious moment a kind of collaboration, a dialogue between the witness inside the room and the data on the walls. We're not just inhabitants of this reality, we're participants in its continuous creation. Each question we ask, each measurement we make, is a stitch in the ongoing tapestry. This idea is unproven, but it offers a place for meaning within the machinery. It suggests our deepest inner experience, the light of awareness, might be mirrored in the deepest outer structure of the cosmos. We're not strangers in a strange room. We might be the room learning how to see. Einstein and Hawking took us right to the edge. They gave us the math for gravity so intense it captures light, and they showed us black holes aren't completely black. But their work stops there. It stops at the edge. General relativity describes the bending of spacetime, but it breaks down at the center. Quantum mechanics describes the particles, but it can't describe the space they are in. To look past that edge, to ask if our universe is inside such a place, we need something new. A language that can talk about warped space and quantum chance together. That's the search for quantum gravity. It's the biggest open question in physics, and it's the only way we could ever understand our own cosmic address. Think of it like a translation guide. We have two incredible books about reality. One book from Einstein is about the shape of the cosmos, the hills and valleys of spacetime. The other book, from Bauer and Heisenberg and others, is about the actors on that stage. Their quantum entanglements, their uncertainties. The problem is the books are in different languages. They're telling the same story, but the stage directions and the plot don't line up. At a black hole's event horizon and at the start of the Big Bang, the two stories crash into each other. The stage becomes an actor. The actors define the stage. To read the full story, you need one book. This isn't just theory, it's a call to observation. The new telescopes, the new detectors, they're listening for this new language. The James Webb Telescope isn't just looking at early galaxies. It's looking back toward the beginning, searching for chemical traces from the cosmic dawn, traces that might have been set by quantum gravity. Gravitational wave observatories like LISA will be. They're not just listening for black holes colliding. They're mapping the vibrations of spacetime, listening for a hum from the very start, a tone that might come from a bounce. These machines give us the data, the raw sounds, The theorists and mathematicians, their job is to build a framework that can hold it all. They work with ideas like string theory, where particles are tiny vibrating loops, or loop quantum gravity, where spacetime is woven from threads. These are candidate languages. They try to describe what happens when a star collapses past the point of no return. Not as an ending, but as a change. Their equations have to connect the impossible density of a singularity to the explosive growth of a new cosmos. They have to show how the information from one universe is preserved and translated and projected into a new one. It's the math of a caterpillar becoming a butterfly if the caterpillar was a star, and the butterfly was everything we see. So finding our place isn't about picking an existing idea. It's about creating the new physics you need to even ask the question right. The idea that we live in a black hole. It's more than a guess, it's a test. A challenge. It demands a theory that can do what Einstein's and Hawking's could not. Look at the origin and see not a wall but a door. This pursuit, it's the human journey. It's us looking at the sky and refusing to believe the deepest questions have no answers. We're driven to write the next physics chapter because by doing that, we might finally read the return address on our own existence. We've been through a lot of ideas, the one-way street of the event horizon, the holographic projection of reality, messages in ancient light, the philosophical tremors of a nested cosmos, and the possibility that we might be living inside a black hole's event horizon. It's more than speculation. It's a rigorous hypothesis. It challenges our deepest assumptions about existence. It connects the largest scales of the cosmos to the smallest scales of quantum gravity. And it could solve puzzles that have troubled physicists for decades. The arrow of time, the dominance of matter, the accelerating expansion, the profound silence of the cosmos, each one could be a clue, a feature of the room we inhabit. Not a fundamental mystery of an infinite, open universe. Definitive proof might stay elusive. It might be hidden forever beyond that one-way boundary. But the value is in the questions. They push the boundaries of science and imagination. They force us to look at evidence with new eyes. The cosmic microwave background isn't just a relic anymore. It's a potential message. The missing magnetic monopole isn't just an annoyance. It's a potential signature. The universe's fine-tuning isn't just a lucky break. It could be a cosmic legacy. This idea reframes our place. We aren't necessarily the central characters in a universe made for us. We might be witnesses. In a cosmos that exists for a different purpose, to replicate, to transform, to continue a chain of realities, a chain that stretches beyond our comprehension. That perspective is humbling, but it's also unifying. It suggests that every star that dies, every black hole that forms, that's not an end, it's a potential beginning. The matter that makes you was forged in stars, but those stars themselves might be the grandchildren of a stellar collapse. In a forgotten cosmos, you are not just stardust. You are the legacy of an infinite lineage of transformations, a conscious spark in one chapter of an epic with no final page. So look up at the stars tonight and wonder. Are you looking at the distant glow of other galaxies? Or are you looking at the interior of a cosmic tomb that is also a cradle? Is the vast darkness between them empty space? Or is it the curved shape of the room itself? The questions change everything. Even if the answers stay out of reach, they turn the night sky from a passive backdrop into an active story. A story we are still learning how to read.